In this section of Unit 2, we're actually going to be solving exponential and logarithmic equations. Some students prefer this section the best because they're looking for a specific answer. It's not a concept, it's something that you can actually physically touch and think about. And there are going to be two different methods that we use. The first one we're going to talk about in exponential equations are the one-to-one property. This is something that it's a technique that's been around for a long time. Books had kind of gone away from it, and now they're back to using it. And I'll show you a couple examples. But you can use a one-to-one property if the bases are the same. So this is a to the x equals a to the y. Then x equals y. Seems very simple. The problems can get more complicated. So there's a specific order that I want you to follow in this. So my first example, I have 25 to the x power equals 125. So you can see the bases are not the same. One is 25 and another one is 125. But that's the wonderful thing about mathematics is we can manipulate this. You have to know your numbers. You have to have a good number sense to really do well at this section. So 25, I know I can rewrite as 5 squared. 125 is 5 cubed. Now I have the same base. From here it's algebra. When you raise to a power, you multiply. So I have 5 to the 2x equals 5 to the third. Now I can write the exponents equal to each other. So 2x equals 3. And I'm going to solve for x, so x is equal to 3 halves. And during the live lesson, I will show you, I want you to check it using your original equation, and I'll show you how I do that with the calculator. Another example is I've got 8 to the x minus 1 is equal to 32 to the x plus 4. So I have to think in bases. And 8, I can rewrite that as 2 to the third power. 32 is 2 to the fifth power. So for some people it makes it easier if you write out all your exponents that you know about. When you raise to a power, you multiply. So 2 to the 3x minus 3 equals 2 to the 5x plus 20. And be careful at this step, because even though I know you know how to multiply, this is typically the step that students would make the mistake at, and they just forget to distribute. Now that the bases are same, I know my exponents have to be equal. And I get x is equal to negative 23 over 2. And I would check that. The other one we're going to use is inverse property. So this is the kind, if a to the x equals y, then I can rewrite the inverse, which is log base a of y equals x. And here's the steps that I use for this as well. So my first example, I have 3 to the x plus 4 equals 10. I always check to see if I can use the one-to-one property first, and there's no way I can make a 10 to a base of 3. So then I know I have to use the one-to-one property. So I have to write the equation so the exponential term is isolated. In this case, the exponential term is isolated. 3 to the x plus 4 has nothing on the outside of it, nothing multiplied by it, nothing added or subtracted from it. So I can rewrite this exponential equation as a logarithmic equation. So I have log base 3 of 10 equals x plus 4. I would solve for the variable, so I'm going to subtract 4. So I have log base 3 of 10 minus 4 is equal to x. Now be careful. This 10 is what you want to take the log of, not the 4. So I would have x is approximately equal to negative 1.904. If you're doing a multiple choice test, sometimes quizzes, Delta Math, something like SATs, if they're looking for the exact form, this would be the exact form here, and this would be the approximate form. I am looking for the approximate answer because I want to make sure that you can also use a calculator to plug it in. My next example, 2 times 5 to the 3x minus 4 equals 17. So in this case, I have a 2 being multiplied by this exponential term. Do not multiply the 2 and the 5 together. You cannot multiply a number by an exponential term. So I have to divide by 2. Now my exponential term is isolated, so I'm going to rewrite the equation. So I have log base 5 of 17 over 2 equals 3x minus 4. I'm going to add 4. And I'm going to divide by 3. And this is, there's several different ways you could see this. This is how I like to think of it. I want all of this divided by 3, which is the same thing as multiplying by 1/3. If you don't like that, you could divide by 3. It doesn't matter. That's the exact answer. My approximate answer is going to be x is approximately equal to 1.777. Logarithmic equations also have the same 2 processes. And the one-to-one property is truly very simple, and a lot of students tend to forget to even use the one-to-one property. But in solving logarithmic equations, if you have a logarithm base a of x equals logarithm base a of y, then x equals y. And these bases have to be the same, and I'm not going to give you any problems where they don't. So my first example, I have log base 2 of 3x minus 7 equals log base 2 of x plus 1. Since this logarithm equals this logarithm, I know that 3x minus 7 has to equal x plus 1. Solve for x, I get 2x is equal to 8. I get x is equal to 4. And I would check that again in my original equation. My next example, log x plus log x minus 5 equals log 6. Okay, just looking at this, it doesn't look like I could use a logarithm equals a logarithm, but I can. I'm just going to have to condense the left side of the equal sign. So since this is being added, I'm going to multiply. So I'm going to multiply x times x minus 5. Now I can do the one-to-one property. So I have x squared minus 5x equals 6. This is a quadratic, so I'm going to set it equal to 0. And that's important. You have to show that you're setting it equal to 0. This is going to factor. So I get x is equal to 6, and I get x is equal to negative 1. When I check these back in the original equation, negative 1 will not work. So the only answer I have is x equals 6. Negative 1 is an extraneous solution. So that's why it's really important that you check your work, not only to check for your mistakes, if you've made any mistakes, but also sometimes you do all the right steps and there isn't a solution or there's an extraneous solution, so you have to be careful. Okay, we also have the inverse property. So once again, this is if a to the x equals, oops, you know what? We're going to do it, I have to retype this. If log base a of y equals x, then a to the x power is equal to y. So that's a mistake I've made on my notes. Okay, so first I'm going to write the equation so the logarithmic term is isolated. So this log is by itself. So the first example, I have 2 log base 3 of x minus 4 equals 10. I want to get this log base 3 of x minus 4 by itself, so I'm going to divide both sides by 2. I could have taken the 2 and put that as an exponent, but you will see that that then becomes, it creates problems. You're going to create extraneous solutions, and I don't want to do that. So now that I have a logarithm equals a number, I'm going to rewrite it as an exponent. So 3 to the 5th equals x minus 4. So I have x is equal to 4 plus 3 to the 5th. So x is equal to 247. And I would check this in the original equation. My next example, I have log 4x minus log of x minus 7 equals 3. And notice I don't have a base here, so that base is going to be 10. I have a log minus a log, but it's not equal to a log, so I cannot use the one-to-one property. But I can condense this left-hand side. Now I can rewrite it as an exponent. So I have 10 to the 3rd equals 4x over x minus 7. Just switch it around. And 10 to the 3rd is 1,000. I'm going to cross multiply. Subtract 1,000x. And x is going to equal 7,000 divided by 996. And I'm just going to write that as in decimals, 7.028. And once again, I would check it, and I will show you during the live lesson how to check it in a little bit, in a few more examples.